Hi there, and welcome to the second part of my talk on the amplified warming of extreme temperatures over tropical land. At the end of part one, I discussed this simple take-home message, which is that hot days over land are expected to warm more than the average day because those days are dry. And this dryness limits increases in specific humidity, meaning that larger temperature increases are needed on those hot land days to compensate. So now I'm going to take this simple idea and use it to develop a quantitative theory to understand the amplified warming of extreme temperatures over tropical land. So the basis for this quantitative theory is the assumption which we made in part one of equal changes in percentiles of moist static energy over land and ocean. So what I'm assuming is that delta HL, so the change in moist static energy over land at a percentile P, is equal to the change in ocean moist static energy at that same percentile P, where P is a given moist static energy percentile. And I showed this figure previously, and this indicates that for about the 50th percentile of moist static energy and above, changes in percentiles of moist static energy over land and ocean are approximately equal. So this ratio of land changes to ocean changes plotted here for moist static energy is about 1. And that's supporting this assumption of equal changes in moist static energy over land and ocean. Okay, so how can we use this constraint on moist static energy changes to construct a theory for the response of land temperature to climate change? So the first thing I do is I consider the moist static energy of hot days exceeding the xth percentile of land temperature. So I define that moist static energy to be H sub L for land with an X, and that's the moist static energy of all days exceeding the xth percentile of land temperature. And that's just equal to the temperature, Cp times the temperature of those hot days, plus L times Q, or specific humidity on those hot days. So how does this moist static energy of hot days change with climate? So to estimate the change in moist static energy on these hot days, I define Px to be the moist static energy percentile corresponding to those hot land days. So we can define Px is defined as the moist static energy, the Px percentile of moist static energy is defined to be equal to the moist static energy on those hot land days. So to give you some intuition into what this Px is, here I'm plotting this moist static energy percentile Px, which corresponds to the moist static energy of days exceeding a given temperature percentile. So first I'm plotting this quantity over ocean for the historical simulation. And what we see is that there's a very straightforward relationship between this moist static energy percentile Px to which the moist static energy on days exceeding a given temperature percentile over the ocean correspond. So we see almost a one-to-one relationship between these quantities, which indicates that over the oceans, hot days have a larger moist static energy and correspond to higher percentiles of the moist static energy distribution. And that's because relative humidity tends to be fairly uniform over the oceans and doesn't change much from day to day. So over the oceans, higher temperatures and higher specific humidities go hand in hand, meaning that higher temperatures over the ocean and higher moist static energies also go hand in hand. So that's over the ocean, but over land it's a very different story. So over land, hot days tend to be drier, meaning that relatively speaking, hotter days over land tend to have lower moist static energies than, say, the median land day. So if we look at, say, the 95th percentile on the x-axis, so the moist static energy of days exceeding the 95th percentile of temperature, so the 5% hottest days have a moist static energy that's lower than the median day. And this is because hotter temperatures over land tend to coincide with drier conditions, meaning that you tend to actually have a relatively small moist static energy on those hot days. Okay, so that's what this Px percentile means. So we map the moist static energy of hot days to some percentile of the moist static energy distribution, Px, and then we assume that the moist static energy of those hot days increases at the rate of that Px percentile. So we can link changes in moist static energy of those hot land days to changes in the Px percentile of moist static energy over the ocean, and that's written here in equation form. So now we have an equation linking the temperature, the specific humidity on hot land days to the change in ocean moist static energy for the Px percentile. So we can rearrange this equation and get the change in temperature on the left-hand side, and this gives us a very simple theory for the land temperature change of days exceeding the x percentile, so delta Tx. It's just equal to 1 over Cp, which is the specific heat capacity of air at constant pressure, times the change in ocean moist static energy, minus L, which is the latent heat of vaporization of water vapor, times the change in specific humidity on those hot land days. This is a very simple theoretical prediction for the land temperature change. So how does it work? So if we apply this very simple theory to the simulations, we see that it doesn't do particularly well. In particular, for the high percentiles of temperature that we're really interested in, this very simple theory overestimates the temperature response quite substantially. So for days exceeding the 95th percentile of temperature over land, this simple theory overestimates the response by about 0.5 degrees Celsius, which in fractional terms is quite a big error. So this very simple theory overestimates the warming of hot land days. So why is this theory going wrong? What are we missing? And can we refine this theory to make it more accurate when we apply it to the simulations? So what this very simple theory is missing is it's missing an extra component to the moist static energy change on hot days associated with those hot days becoming relatively less energetic as climate warms. So when I developed the simple theory in the previous slide, I assumed that the moist static energy of hot days increases in line with the corresponding percentile of ocean moist static energy. So I assumed that delta H on days exceeding the X percentile was just equal to delta the change in ocean moist static energy at the Px percentile. But that assumed that the moist static energy percentile to which hot land days correspond itself stays constant as climate changes. But what I found looking at these simulations is actually hot days over land become relatively less energetic as climate warms. So this means that the Px percentile to which hot land days corresponds actually decreases as climate warms. So if you remember, I showed this figure previously, which showed that over the ocean there's a very tight relationship between temperature percentile and moist static energy percentile. Over ocean, hotter days have higher moist static energy. But over land, that's not the case, where the very hottest land days actually have a moist static energy approximately equivalent to the median day. So these are the curves for the historical simulation. If we look at the SSP 245 simulation, which is a simulation of a warmer future climate, we see that over the ocean not much changes, but over the land, the dashed line is the future warmer simulation, and we see that particularly for hot land days, in a warmer climate, those days become relatively less energetic when you warm the climate. So in the historical simulation, the 5% of the hottest 5% of land days corresponded to about the 54th percentile of the moist static energy distribution. But in the SSP 245 simulation, the hottest 5% of land days only corresponded to about the 48th percentile of moist static energy. So although moist static energy is increasing for all days over land and ocean, for the hottest days over land, it's not increasing as much as the median day. So that the relative moist static energy of those hot land days is actually declining as climate warms. And this turns out to be an important influence on the temperature response of those hot land days. So how can we quantitatively account for that relative decrease in the energy of hot land days in our theory? So to do that, I include an extra term, capital delta H, to account for the fact in these simulations that hot land days become relatively less energetic as climate warms. So my theory just changes slightly. Now the change in the moist static energy of those hot days is equal to the change in the ocean moist static energy at the px percentile plus this delta H term, where delta H is equal to the difference in moist static energy in the warmer simulation between the px percentile and the px plus delta px percentile. So that delta px is the change in this moist static energy percentile to which hot land days correspond. So hot land days become relatively less energetic as climate warms, which means that delta H is actually negative. So this is a tempering influence on the response of the energy on hot land days to climate change. And the reason why hot land days become relatively less energetic as climate warms is because they become drier with warming. So we can estimate delta H in terms of changes in relative humidity on hot land days relative to changes in relative humidity averaged over all days over land. And I won't go into the details of how we do this estimation. You can look in details on the preprint that I'll show the link to at the end of this talk. But what I come up with is we can estimate delta H fairly simply as a function of L, which is just the latent heat of vaporization, times the change in relative humidity, R, on hot land days, times the saturation specific humidity, QL_SAT, on those hot days, relative to the change in relative humidity averaged over all days, times the saturation specific humidity averaged over all days, where averaging over all days is indicated by these overlines. And what we see in the simulations is that this relatively straightforward estimate of delta H captures what's going on in the simulations quite well. So we can estimate this relative decrease in energy as a function of changes in the relative humidity. Okay, so now we add this estimate for delta H into our theory. So now on the left hand side we still have the change in the temperature of days exceeding the xth percentile over land. So that's what we're interested in predicting as a function of these various terms on the right hand side. So all I do now is I express the changes in specific humidity on the right hand side in terms of changes in temperature and relative humidity, and I rearrange and I come up with an estimate of the land temperature change as a function of various quantities on the right hand side of this equation. So according to this theory, the response of the land temperature above a given percentile x of temperature depends on changes in ocean temperature, and also changes in land and ocean near surface relative humidity. And these various terms have red squares around them. So these are the quantities that influence the response of land temperature. The temperature response is also influenced by 4 different sensitivity parameters, which define the sensitivity of land temperature to changes in ocean temperature or land relative humidity or ocean relative humidity. And the important thing to note about these sensitivity parameters is I haven't given you the equations for them here, but they're physical parameters. They're not statistical fits. They're part of the physical theory, and they depend only on physical constants and climatological quantities. So these sensitivity parameters don't depend on you running a climate change simulation. They're just a function of the basic state and physical constants. Okay, so that's the theory. So let's return to the simulations and see how the theory does. So here is the figure I showed previously, showing the temperature change on the y-axis over land in red and ocean in blue for days exceeding a given temperature percentile x on the x-axis. And now I can apply this theory, which is the black dashed line here, and we see that the theory does pretty well at capturing the temperature change across most percentiles over land. So this theory, based on the fairly simple assumption of uniform changes in moist static energy across the tropics, quite accurately captures what's going on in these simulations. Okay, so we can also look at the scaling factor, which I introduced earlier. So remember, this is the ratio of the temperature change for days exceeding a temperature percentile x divided by the average temperature over all days. And we see strongly enhanced warming over land for higher temperature percentiles. We can apply the theory, and it's not perfect, but it qualitatively captures the simulations again, and in particular, it captures this strongly amplified warming of the hottest temperatures on the right relative to the average temperature on the left. Okay, so everything I've been showing so far has been multi-model means. The theory also captures the vast majority of the variance across models in the temperature responses. So here I'm showing the temperature change for the 5% hottest land days. The theory is on the x-axis and the simulated changes are on the y-axis. And we see that there's a strong correlation between the two. So the theory can explain why different models produce different temperature responses at high percentiles. So indicating that this theory looks to be a useful tool for understanding why different models produce different extreme temperature responses, and could be used potentially to narrow uncertainty in these responses. Okay, so this is the full theory, which does well at explaining what the simulations are doing. We can think about a simplified version of the theory. So a simplified version of the theory pops out if you assume, as is often typical in climate science, that relative humidity is approximately constant under climate change. So this is an assumption that's made quite frequently in climate science, and often it's a pretty reasonable assumption to make. So if you make that assumption, the theory boils down to a very simple equation. It shows that the change in temperature over land over some temperature percentile x is just equal to the sensitivity parameter gamma TO times the change in ocean temperature. So it's a very straightforward equation. And how does this do when we apply it to the simulations? So here I'm showing this fixed relative humidity version of the theory applied to the simulations as the dotted line here. And we see that again, it's not perfect. It doesn't capture exactly what the simulations are doing, but it does capture a key feature of the simulated land temperature responses, which is this amplified warming of hot days. So that's a result that doesn't rely on changes in relative humidity and can be predicted just as a function of the ocean temperature change and this gamma parameter, which just depends on quantities in the control climate and physical constants. So specifically, gamma is equal to Cp plus L times alpha, where alpha is the Clausius-Clapeyron parameter, times as the specific humidity over ocean, QO, divided by Cp plus L times alpha times specific humidity over land. So because the specific humidity near the surface over ocean is larger than over land, this sensitivity parameter gamma is always bigger than 1. And this is the essential reason why hot land days warm more than the average day. Because for hotter days, the specific humidity over land is increasingly small, meaning that the sensitivity parameter is increasingly big. And this is the origin of the drier get hotter mechanism. So the contrast in specific humidity QL and over land and ocean and QO is stronger for hot days because those days are drier. And this leads to amplified warming of those hot days relative to the average day. And this is a prediction based on properties of the current climate. So if you know this gamma parameter, you can predict this amplified warming relative to the mean temperature and relative to the ocean without running a climate model. And we can plot out this sensitivity parameter, and what we see is that for higher temperature percentiles, this sensitivity parameter is increasingly large because Q over land for those hot days is increasingly small. So this is essentially the drier get hotter mechanism. Okay, so that's the fixed relative humidity theory. But if we apply this fixed relative humidity theory to predict the absolute changes in land temperature, which is the dotted line here, we see that we underestimate the land temperature response quite substantially. So changes in relative humidity over ocean, but particularly over land, strongly affect the magnitude of the land temperature response, even if they're not essential for understanding this amplified warming of hot days relative to the average day. Okay, so we can go back to the full theory and look at the various components of the total temperature response. So the full theory, the total response is in black, And then the cyan line is the contribution due to changes in ocean temperature. The blue line is the contribution due to changes in ocean relative humidity, which is small but does contribute to the warming. And then in red is the contribution due to changes in land relative humidity. So land relative humidity tends to decrease as climate warms, and that tends to enhance the warming across all percentiles. So if you want to understand the response of not only extreme temperatures but also average temperatures over land to climate change, you really need to understand changes in relative humidity. So there's this very tight coupling between changes in relative humidity and changes in temperature over land. Okay, so just to summarize, so I've introduced a theory to understand the amplified warming of hot days relative to the average day over tropical land. This theory is based on the assumptions of active convection and weak temperature gradients in the tropical free troposphere. And these two assumptions combined place a strong constraint on changes in moist static energy. I use this constraint to develop a new theory for the land temperature response across all percentiles, and this does well at capturing the magnitude of the warming in models and also differences in the land temperature response across models. So there's some hope that this theory could be used to identify the processes leading to divergent land temperature responses across models and could provide motivation for making these projections of extreme temperatures in the tropics more reliable. The theory predicts that amplified warming of hot land days there is amplified warming of hot days because those days are dry, but changes in relative humidity are also important for understanding the magnitude of the warming overall. So that's it. A preprint of this research is available online, so you can just Google amplified warming of extreme temperatures over tropical land and you'll get to it pretty quickly. And yeah, I hope you enjoyed learning about this research. Please feel free to get in touch by email if you have any comments or would like to discuss the work further. So thanks very much.